Assalamualaikum warahmatullahi wabarakatuh and a very good morning. I am Muhammad Amin bin Muhammad Amir from 4AM4. So today I would like to explain to you about rotation of loop in a magnetic field and a waveform produce, and operation and construction of revolving armature and revolving field type AC generators. Okay, first of all I would like to explain to you how rotation of loop produce. The turning of a coil in a magnetic field produces motional EMF in both sides of the coil, which add. In terms of Faraday's law, when you see that the rotation of the coil continually changes the magnetic flux to the coil and therefore generates a voltage. Since the component of the velocity perpendicular to the magnetic field change sinusoidally with the rotation, the generated voltage is sinusoidal or AC. For the second slide, operation and construction of revolving armature and revolving field type AC generators. It's similar in construction to a DC generator. The rotor rotates in a fixed field with the EMF peak via slip rings. The rotor beam windings are laid in slots along the rotor periphery. The armature laminated to reduce eddy current loss. Armature type of generator place the field coils in the stator and place the armature coils in the rotor. In the setup, the magnetic field is stationary and the coils that induce a voltage is rotating. This type of generator is usually used in DC generator systems, since it is impossible to have a DC output from the stator. So this is a diagram of operation and construction of revolving armature. Okay, next is operation and reconstruction of revolving field type. From the word itself, that means that the field coil that produce magnetic field is located in the rotor and being moved by a prime mover action. This is completely opposite to the rotating field type of a generator, but this is the most common type of AC generator used in industry. As described in the diagram, the excitation system is supplying DC power source to the rotor through the brush contacts. The frequency of the alternating voltage generated in the stator winding is proportional to the number of poles in the rotor field and the speed of shaft rotations. So this is a diagram of the rotating field generator.
Hello, good evening everyone. I'm AFIQ UZAIR from 4AM7. Today I'm going to talk about single phase alternator, two phase alternator, three phase alternator, star and delta connection. Single phase alternator. Single phase alternator has a stator made up of a number of windings in series, forming a single circuit in which an output voltage is generated. Figure 95 illustrates a schematic diagram of a single phase alternator having four poles. The stator has four polar groups evenly spaced around the stator frame. The rotor has four poles with adjacent poles of opposite polarity. As the rotor revolves, AC voltage are induced in the stator windings. Since one rotor pole is in the same position relative to a stator winding as any other rotor pole, all stator polar groups are cut by equal numbers of magnetic lines of force at any time. Two-phase alternator. Two-phase alternator have two or more single-phase windings spaced symmetrically around the stator. In a two-phase alternator, there are two single-phase windings spaced physically so that the AC voltage induced in one is 90° out of phase with the voltage induced in the other. The windings are electrically separate from each other. When one winding is being cut by maximum flux, the other is being cut by no flux. This condition establishes a 90-degree relation between the two phases. Three-phase alternator. Three-phase alternator or polyphase circuit is used in most aircraft alternators. Instead of a single or two-phase alternator, the three-phase alternator has three single-phase windings spaced so that the voltage induced in each winding is 120 degrees out of phase with the voltage in the other two windings. A schematic diagram of a three-phase alternator showing all the coils become complex and difficult to see what is actually happening. A simplified schematic diagram showing each of three phases is illustrated in Figure 936. The rotor is omitted for simplicity. The waveform of voltage are shown to the right of the schematic. The three voltages are 120 degrees apart and are similar to the voltage which would be generated by three single-phase alternators, whose voltages are out of phase by angles of 120 degrees. The three phases are independent of each other. Star connection and delta connection. Star connection. In a star connection, phase voltage VPH equal VL. Since the induced in EMF in the primary winding of an alternator is directly proportional to the number of turns, a star-connected alternator will require less number of turns than a delta-connected alternator for the same voltage. For the same line voltage, a star-connected alternator requires less insulation than a delta-connected alternator. Due to the above reasons, three-phase alternators are generally star-connected. In star connection, we get three-phase and four-wire system. This permits the use of two voltage, phase voltage as well as line voltage. Single-phase loads can be connected between any one line and neutral wire, while three-phase loads can be put across three lines. Such a feasibility is not available in delta connection. In star connection, the neutral point can be earthed. Such a measure offers many advantages. For example, in case of line to earth fault, edge fault, the insulators have to bear 1/3 times the line voltage. Earthing of neutral also permits the use of protective device to protect the system in the case of ground faults. Delta connection. This type of connection is more suitable for rotary conveyors. Most of three-phase loads are delta connected than star connected. One reason for this, for the case of unbalanced load, is the feasibility with which loads may be added or removed a single phase. This is difficult to do with star-connected three-wire load. Most of the three-phase induction motors are delta connected. This is the difference between star and delta connection. Thank you.
Hello, Assalamualaikum. My name is AHMAD Luqman. Today in this video I want to present to you how to calculate the line voltage, phase voltage and currents, and how to calculate the power in a three-phase system in the AC generator. Okay, let's go to the slide. Okay, let's see how we can calculate the line voltage, phase voltage and currents, and also how to calculate the power in a three-phase system in the AC generator. Okay, let's go to the next slide. Okay, in the delta connection, you can see the phase voltage is equal to line voltage. Phase voltage is equal to line voltage. If you get the phase voltage, you also can get the line voltage too. To get the line current can get from the current that are flowing in the two windings that are connected to that particular line. Okay, you can get here. The line current is square 3 times phase current. In this delta connection, there are no neutral connection. Okay, next is a star connection. In the star connection, there are a neutral connection that is here in the middle of the three of this. Okay, to get the line, and then the line current is same with the phase current. Like this is the line current, and this is a neutral current, a neutral line. To get the line voltage is square 3 times phase voltage, and then you can get the line voltage. The end of each winding is neutral. The end of this winding, this three winding is neutral. If you can see in the picture here. Any line to the neutral is called phase voltage. any line to the neutral line. This is a line. This is the line. This is a neutral. This is a phase voltage. Here to here is the phase voltage. This line to this neutral called phase voltage. Any line to line is called line voltage. This line to this line we can call it line voltage. This line to this line voltage. Okay. And then how to calculate power in a three-phase system. Okay, to calculate the power in a single-phase system, we must use this formula: voltage times current times cos theta watts. You can get the true power of a single-phase system. True power in a balanced three-phase star or delta system is 3 times of a single-phase system. To get the true power from the three-phase star or delta system, we must times 3 from the true power of the single-phase system. In a three-phase star, we can use this formula: 3 times phase voltage times phase current times cos theta watts. In the delta system, we can use square 3 times line voltage times line current times cos theta watt, and you can get the true power in the three-phase system. Okay, that's all. Thank you.
Hey, good morning and assalamualaikum to everyone. My name is MASKOZ and I'm from 4AM7. Today I would like to explain you about voltage regulation and permanent generator. Okay, let me start with our session at my slide. Let me start with our topic, which is permanent generator and voltage regulation. Before we start about our topic, I would like to explain more into detail about AC generator. The purpose of AC generator is a main electrical power source in large aircraft, and they have two component part in AC generator, which is the rotor and stator. The function of rotor is the rotating part, which is turned by aircraft, and the function of stator is to fix part of a generator. Okay, finish. Okay, permanent generator. It be using as a type part of most brushless AC generator. Commonly it using by many largest aircraft such as Boeing and A330 and ATC. A permanent magnet generator is a device that convert mechanical energy to electrical energy. This device do not require a separate DC supply for the excitation circuit, or do they have slip rings and contact brushes? Yeah, this one is the slip rings. The PMG can be a DC voltage machine with brushes and rotary collector, or much more frequently an asynchronous multi-phase machine, whereas the starter and rotor magnetic fields are rotating at the same speed dalam kelajuan sama. Considering a permanent magnet DC generator, then the inductor will be found at the starter with an array of permanent magnets. But in case of an AC generator, the inductor is located at the rotor with an assembly of permanent magnets. And finally, coil armature is on the starter as output. Okay, finish. I will explain about voltage regulation. The voltage regulator section of the 3-unit regulator is used to control generator output voltage. If the regulator senses that system voltage is too high, the relay points open and the current in the field circuit must travel through a resistor. Okay, the voltage regulator monitors generator output and controls the generator field current as needed. The resistor lowers field current and therefore lowers generator output. Okay, I will show you the picture. Okay, if you see the picture above, the voltage coil is connected in parallel with the generator output, and it measures the voltage of the system. If voltage get beyond a predetermined limit, the voltage coil become a strong magnet and open the contact points. If the contact points are open, field current must travel through a resistor, and therefore field current goes down. Since this voltage regulator has only two positions, which is points open and points closed, the unit must constantly be in adjustment to maintain accurate the voltage control. During normal system operation, the points are opening and closing at regular intervals. This type of regulator is sometimes referred to as a vibrating type regulator. As the points vibrate, the field current rises and lowers and the field magnetism average to a level that maintains the correct generator output voltage. If the system requires more generator output, the points remain closed longer and vice versa.